another 2 months or so. Maybe this is my last presentation of a lecture in this way. It's actually very nice to welcome you to today's lecture. Henk is on the way to become a Bitladen professor, and it's actually a long time ago we last had a lecture like this for Bitladen professor. I can't even remember when it was. So we have to send lectures quite often. But for Bitladen professor, it has been a while since. But I know we have a number of people in line for this for the next year or so. So there might be a few more in the future. But today it's Henk. So the formal procedure is that we at the department suggest people for promotion in our yearly planning process. And Henk was suggested 1 year ago with the plans that we handed in 2014, if you remember correctly. And then Henk had to apply. Well, then this position was decided for Henk, and he had to file an application and has been evaluated by experts. All that has now been done. The recruitment committee came to the conclusion that he fulfilled all the qualifications needed to become Bitladen professor. And the last thing that he has to do is what he will do now in the next hour or so, to give a presentation of some of his work, so we all can learn what he's doing and maybe also what he's intending to do in the near future. So with this short introduction, the floor is yours, Henk. We are looking very much forward to listen to your presentation.
Okay. Thank you, Arne. Thank you all for coming. I'm happy to see people not just from our own division, but also from the other divisions and even from other departments. So welcome. So this talk will be on I put a title, The Role of Wireless Communication in the Future Intelligent Transportation Systems, but that's not really what I will talk about, but at least you're here, so you can no longer escape. I will talk about today about macroscopic traffic control. I will talk about how we can modify the city's infrastructure to improve transportation and how communication plays a role there. The work I present is joint work with Balázs, who's sitting in the back from the automatic control group, Ali Zaidi, who's now at Ericsson, Hamed Farhadi, who's now at Harvard, Attila Erilmaz from Ohio State University, and Demis, whose full name I will not pronounce. So what are the trends for future transportation? One thing that we notice in many cities around the world, and also in Gothenburg, is that more and more people are gravitating towards cities. And I think especially in Gothenburg, we will see this over the next decades. We'll see a huge influx of people. Okay, this has many good sides and many bad sides, but it puts a strain on our transportation systems. If we think about Korsvägen, one of our most busy intersections, we cannot put more roads there. We cannot make the roads wider. We cannot do much at all. Okay? So all we can do is either wait for the worst to happen, which is massive traffic jams over the coming years, or we do something smarter. Okay? So we want to avoid having everybody being stuck in a gridlock all the time and do something smarter. So how does wireless communication, how can it help? So my future research will be to a large extent on the use of communication for future intelligent transport. And this can take on many different shapes. It could deal with autonomous cars. It could also deal with infrastructure. So I will talk about one slide on 4 areas, and then I will go in depth in one of those areas. So I believe that communication can help in positioning. As we move towards new wireless communication standards using massive bandwidth and massive antenna arrays, we can leverage this for high accuracy positioning. And I will spend one slide on this. I think communication, of course, plays a pivotal role in autonomous transport in general, where cars can help each other to solve certain tasks. And in order to do this, we need very fast communication, because cars are actuated at very high rates. Communication needs to be very reliable. So in contrast to communication for watching a YouTube movie, if you miss a frame of your movie, it's fine. If you miss a packet, maybe an accident occurs. It needs to be scalable. We have to think about very large-scale communication among many, many entities. So this is one of the areas that we will work on. Another area is microscopic traffic control. So here we're thinking of actuating multiple autonomous vehicles so that they coordinate their actions in a meaningful way to optimize, say, efficiency and also to be safe. And finally, and this will be the area that I'll spend most of the talk about today, is macroscopic traffic control. This work is carried out within the context of a number of projects. So some of these have already completed, some of these are still going on, and these are some of our partners and also funding agencies. Okay, so I would say that right now there's a lot of interest in this, both from industry and the funding agencies, and I think this interest will likely increase in the coming years. When I talk about topics like these all across the world, people tend to be very excited. Maybe it's because I'm excited, I don't know. Okay, so the first area, and I put some of the people that work on these topics, so and most of these should be in the room, so you can ask them. So if you have questions about these, you can ask these people. So I believe that in the future, when we move towards 5G, so the next generation of cellular communication systems, we will use massive antenna arrays, we will use very large bandwidths, and this will allow us to position devices, like this is a receiver device, very accurately, much more accurately than before, and also to determine their orientation. So I foresee a future, not so long from now, maybe 5 years, where I can position a phone within a few centimeters, and not just position, but also know the orientation in 3 dimensions. Okay. And I believe that the cellular signals that we will use will be able to do this. This is an example of what kind of performance we can expect. So here is a base station centered here, and I'm plotting in a 2-dimensional plane the expected performance of positioning. Okay. And red colors are bad, and the green and blue colors are good. And it turns out, for these kind of communication systems, when you're in the right location, you can estimate your location really, really well. When you're in the wrong location, you cannot estimate your position well at all. And depends how the communication is operating. So this means that there's a very tight connection between communication and localization. That many people around the world are now, they seem to realize this. So I think we're in a good position to operate on the intersection of those fields. The second area is location-aware communication. So we try to use location information to improve communication. So an example that we're working with is using our robot testbed. We put basically multiple robots, we let them move around in an environment, and they want to find the optimal locations to optimize an overall communication objective. So you can imagine a scenario where there's a base station there, a transmitter there sending a video stream, but the distance is too long to send directly, and the robots, they should put themselves in the best location to enable end-to-end throughput. Okay, so I can talk about all day long, but maybe I can show you a movie of some of the recent work that some of our bachelor students have been doing. So there's a transmitter, a base station, and there's 2 robots here, and they should put themselves in the optimal location to optimize end-to-end throughput. And they do this autonomously by solving an optimization problem. See, no wires. So when the transmitter is moving, the robots should re-optimize their location. Okay, they cannot move very fast, so that's why the student is moving a little bit slowly. So these are some of the technical details if you're interested. So since we don't have a real lab to test our algorithms, we use some dedicated facilities here, which is the gym. But we can still get things working. So this was the whole team, including the supervisor, that made this happen. Okay, the third area is microscopic traffic control. So here we're considering, for instance, a problem where you have 2 cars that are approaching an intersection and must coordinate their actions in an optimal way to go through the intersection and not have a collision. Optimal could mean many things. So you would typically formulate some kind of optimization problem where each car has its own objective. So some drivers care more about comfort, some drivers care more about speed, and we can mix all of these in an optimal fashion and let the cars cross through the intersection in a safe way. And here also, communication plays a big role. Okay, the cars need to communicate to coordinate. They need to formulate this optimization problem. This requires communication. They need to solve this optimization problem. This also requires communication. And it also involves positioning because, well, I won't go into detail, but you have these differential equations that dictate the dynamics of the vehicle. So they rely on the state of the vehicles, and the states need to be estimated. Okay, so communication and positioning play a pivotal role here. So these are the first three areas that I just went over very, very quickly. This is the area that I want to talk about in more detail. Okay, and this is the work with Balázs, Hamed, Temis, Attila, and Ali. So what we want to do is to improve traffic flow in cities. And there's many ways that you can do this. So we focus on the infrastructure. How can the infrastructure be modified in a small way to drastically improve traffic flow? And these are some conventional ways of doing this, right? This is ramp metering, which I discovered 2 weeks ago while traveling with Balázs in California. It was actually very funny, so let me tell a little story. I mean, I've driven in California many times, basically being stuck in traffic jams all the time. And I know once I enter a highway, there's these signs. Right? So one vehicle per green, and the light just flashes green, red, green, red, green, red. I always wonder, why are they doing this? Right? And this is actually a technique to avoid congestion on the highway, the main artery, and have a little bit congestion on the on-ramps, which is fine. But I didn't know. And basically, we saw many things like this. So we saw these on-ramp, these meters, lots of traffic lights, smart roads, all kind of very sophisticated things that, as a driver, you don't really notice. But Balázs, being a transportation professional, he was so excited the whole time. It's like, oh, ramp meters, oh, traffic jam, oh, congestion, oh, the loop detectors. He was so excited. Yeah. So for me, it's like, okay, it's interesting. All right, so as I mentioned the first slide in the beginning, urban traffic is predicted to increase in many cities. We cannot build more roads in most places. So we need something non-invasive. So we just want to modify the existing infrastructure a little bit and make everything still work. We want to, well, in our case, see if communication can be leveraged and be something that is future-proof. Right? So right now, there's not many autonomous vehicles. In 2017, there will be a few driving around Gothenburg. But in the future, there may be many. Right? So the legacy vehicles and the autonomous vehicles must be able to interact in a meaningful way. OK, so how does this connect to communication? It's not so obvious, right? So there's a trivial connection, which is that cars will need to communicate information to some server, and the server needs to compute something and then send information back to the car. That's a trivial connection here. There's also a non-obvious connection, which is the following, is that when you think about data networks, how they've been designed for many, many years, you do a lot of optimization, right? You're doing routing of packets and scheduling of links, and it's basically very similar to what happens in traffic. So instead of data packets, you have cars, but you still need to schedule them and route them over the network. So you can look back into the data communication literature, and there's some very old papers, 1992, where these problems have been solved. Okay, so there's a paper that talks about optimal routing and scheduling in data networks by Tassiulis and Efremidis from a long time ago. And I think it's interesting also that this paper was published in Automatic Control, not in a communication journal. But maybe there were no communication journals back at that time. I don't know.
There were a few.
There were a few, but maybe not IEEE. I don't know. Anyways. So, yes. So you can ask yourself, isn't this problem solved? If we just take what the communication people have developed, right, and just replace data packets with cars, and do some other small modifications, things should work. This is what we try to do. Okay? So we try to schedule the cars through a network and route the cars through a network. So the scheduling in data networks, so which links to activate in a network, becomes changing of traffic phases in a traffic light. So how should the traffic light operate? Which road should get red and which road should get green? That's the connection between the two. We want to route packets in data networks, and this becomes a routing of vehicles through a city. So the communication aspects are typically, you have this notion of packets, of buffers, right? So the packets are waiting in a buffer before being sent. You have links and you have rates on links. So you have similar notions in transportation. So the packets become vehicles. The roads are basically the buffers. The cars, while they're on the road, they're waiting to be served on another intersection. The links become basically the lanes in the intersection. And the rates become the flow of cars through the intersection. So you could, in principle, do a one-to-one mapping from wireless communication algorithms to packets, to cars. Okay, so you have this picture of kind of cars going over a network, but you have to be a little bit careful. Okay, because you cannot just use all the concepts from wireless communication in cars, because somehow the similarities don't match up. So if you have in a data network, you send two packets over the same link, they will collide, right? You don't get an acknowledgement, you retransmit, no problem. You cannot do this with cars. You cannot retransmit a car. You cannot do network coding of two cars and get a new car. So these are kind of funny ways that this similarity doesn't hold, but there's also more meaningful ways. So before I go back to cars, what I will do now is I will explain basically these type of algorithms. Okay? So I'll go into some mathematical detail how these algorithms work and what their properties are, and then I will go back to cars. Okay. Is it just me or is it hot in here? Okay, so now there's going to be a few slides of math. I apologize for my parents. Now is the time you can use the internet. All right, so we consider the following problem. We have a network here, a very small network, where we want to send data packets over these links, right? And we just want to do one hop communication. So I just want to send from this link to here and from here to here, one hop. Okay? And then the packets at their destination, they're consumed. Okay, so we have a number of links. Each link has a queue. Okay? And these are the packets that still need to be served. And this queue varies over time. So there's a time here, t, discrete time. Okay. There's also arrivals at each link. So these are exogenous arrivals of packets at this link. Okay. And they arrive with a certain rate, lambda L. So the number of packets per hour, let's say, arriving. On the network, there's a set of feasible schedules. So this you can think in wireless networks, the links that you can activate at the same time. Okay. And because you have interference, you cannot activate all the links at the same time. So for instance, for this simple network, I could activate link 1. Okay, but because link 1 is attached to those two nodes, 2 and 3 have to be 2, 3, and 4 have to be quiet, right? So that's one possible schedule. I could also activate link 2, and then everybody else has to be quiet, link 3 or link 4. But I could also activate link 3 and 4 at the same time, okay, because they don't interfere in this simple setting. So this is the set of feasible schedules. Okay. Every time I have a certain schedule activated, I have associated link rates, right? So when I choose to only activate link 1, I can send data at a certain rate over this link. Because of these rates, I can have an evolution of the queues. Right? So the queue at time t plus 1 over link L will be whatever was there before, minus what is served, plus new arrivals. These are the dynamics of the queues. Right? And the objective here is to find the best possible schedule right now. Okay? So as time goes on, the queues evolve, and based on the queue sizes and the link rates, I need to design the schedule at each time. Okay, so it turns out if you go to these papers from the 1990s, this turns out to be the solution. So what you do is the following. You look at all the queues for each of the links, okay, and then you pick a schedule, S. You compute the rates over each of these links, take a sum of the rates and the queue sizes, and that is your benefit by choosing schedule L. And then you search over all possible schedules. And you just pick the one that gives you the most benefit. And that turns out to be the best thing to do. Okay. And it's kind of obvious, right? You want to prioritize links that have lots of packets waiting, and you want to prioritize links with high rates. This is how you get a lot of the data through to your network. Okay. And it turns out that this is called max weight scheduling, has a very nice property. It stabilizes the network for any set of arrival rates in the capacity region. And the way that I interpret this is as follows. Okay. So this is, let's suppose you only have two links where there's arrivals. Okay. Lambda 1 and lambda 2. So these are the number of packets per hour that are arriving. And this is called the stability region, or no, the capacity region. Okay. So when both of the lambdas are really small, that means very few packets are arriving. Right? That means the network will be empty most of the time. The queues will be very, very low. So the system will be stable. Because the queues are always very, very short. Okay, so it's like when you go to the supermarket and there's nobody there and there's 10 cashiers. This would never happen in Sweden, but you know, that's like the best case, right? When you have higher arrivals, so more packets are arriving at the links, then the packets will need to queue in the links, right? But you will, as long as the arrival rates are within this region, the queue lengths are bounded. So they don't grow over time. They will grow up to a point, and then they will be more or less constant. They will not grow unbounded. When you're outside of this capacity region, the queues are growing unbounded. Okay. Now, it turns out that when you have max weight scheduling, for any set of arrival rates inside of the capacity region, you will have bounded queues. If you had a different kind of schedule, okay, so some naive schedule, then even when you're inside here, inside of the capacity region, it could still be such that your queues grow unbounded. Okay? So this is the nice property of max weight scheduling. Okay. And I know this notion of capacity is very different from the information theoretic capacity, and I will see some kind of interesting properties of these scheduling methods. Okay, this is max weight scheduling. Maybe before I move on, any question? Anything that sounds clear? We will build on this, so if you have a question, you should ask. Yes? It will not assure fairness. This is the only property you can prove. It stabilizes the network, so the queues will be finite. Yeah.
Can you bound the queue to an upper constant also?
I don't know if there's a number that it will be finite, and the number will grow when you're approaching this region.
Right.
But I don't know if you can say this will be the number. It depends on the system, of course.
But in a practical setting, you might want to limit the queue to be less than 100 cars, say.
Yes. Yeah, definitely. I mean, definitely from simulation, you'll be able to see this is what you can get. But I don't know if there's a number that you can put on this. All right. So the problem with this is that this optimization requires the set of feasible schedule, and this is a global problem. What is the set of feasible schedules? Okay. Because all these links interact in some non-trivial way. So this is a hard global problem in general. But if you can solve this, I mean, you can do pretty nice things. Okay, multi-hop. So now we just talked about single hop. Multi-hop, you want to route data over a network, right? From here to there with multiple steps in between. So this is the model now. You have packets arriving at source nodes. So there's a notion of source nodes in the network with certain rates. Okay? Each source has each packet has a source and a destination. Right? Packets with the same source and same destination, we call this a flow. And all the flows with the same destination is called a commodity. And this is the terminology here. A commodity has a certain given destination, but could come from different origins, right? Different sources. Okay, so how we operate in a multi-hop communication is we keep at each node, we keep queues per commodity. Okay, so each node will keep track for each commodity how many packets still need to be served. Right? Even though this destination could be very, very far away. Okay. And of course, if you're the destination for a certain commodity, your queue is 0, right? Because you're basically eating up all the packets as they come. You still have a certain set of control actions. Right? This is like the scheduling before. The links that you can activate at the same time. And with a certain action, there's a certain set of rates. I changed the notation because I followed the notation from the papers. So this is the rate over link from I to j with a certain action I. So when I activate a certain set of links, there will be certain rates. You have a similar evolution of the queues. So the queue at node n for commodity C, as it evolves, is whatever it was before, minus what is going out, plus what is going in from other nodes, plus exogenous arrivals. Okay, so it's a very simple equation. And now what you try to find is what are the best control actions. Right? And the best here will be solved by something called back pressure. So back pressure is a method. It's a simple variation of this max weight scheduling that stabilizes the network within the capacity region. Okay, so it's still optimal in that sense of stabilizing the network. Okay, so I will do one slide with more math, and then I'll do an example, okay, for the many of you that are confused. So this is how the algorithm works, and I just want to show this because it's such a simple and beautiful algorithm. For each link, you choose the optimal commodity. Okay, so each link has a source and a destination. That's a link, right? And you want to send over this link, and you choose what is the best commodity I should send over this link. Okay, so what should I serve? And you do this by computing the differential queue size. So if the destination has lots of packets if my destination has lots of packets for a certain commodity and I don't, then I should get packets, right? Just to balance things. If I have lots of packets and my friend doesn't, then I should send to him. So this is how you find the optimal commodity sent over a certain link. And now you want to account for the rates. Okay, and this is in this last equation. So before we do that, we find the weight for each link. So that's the differential Q size for that optimal commodity. And then we find the optimal control action. That's the same as before. So we look at all possible schedules that we can activate. And for each schedule, we compute the rates. We find the differential Qs. And we take the sum over all of the possible links. And then we maximize. Okay. And this, if you implement this over a network, this is the best thing to do in terms of stabilizing the network within the capacity region. Now, how do you do routing in this network? How do you decide where the packets are going? And this is something that I found very, very strange when I first learned about this algorithm. You don't do any smart routing. So you just send the packets of that commodity over the link based on your schedule. So this means that I'm a certain node. I decide I have packets for different destinations. And I solve this problem, and I just send the packets. Okay? And I don't worry if they're going towards the destination or away from the destination. All I know is that when they arrive at the destination will consume them. So you're doing a kind of very strange routing. The packets will basically go randomly around the network and at some point get to their destination. You don't do anything very smart. But it turns out that this is the optimal thing to do. Okay, and you still need this global knowledge to solve this maximization problem. Okay, so let's make this a little bit more concrete. Okay, this will help. So this is a very small network with 3 nodes. Okay, and there's 2 commodities. There's the green commodity here, so this goes to a certain destination, and the red commodity also goes towards a certain destination. Okay. There's 2 possible control actions I can take. I can either send data counterclockwise or clockwise. That's the only 2 actions I can take. When I send data, I can send over a link, and this link has certain rates. Okay, and here I set all the rates to 1, except for these fat links, the rates are 5. This means when I activate the link, I can send 5 packets here, but only 1 packet here. Okay, just as an example. Okay, so what are the optimal commodities for these links? So let's see from 1 to 2. Okay. If I look from 1 to 2, what are the differential Q sizes? Let me see. Okay, from 1 to 2, I have the green commodity, right? So I have 0 packets here and 3 packets there. I have, of the red commodity, 3 packets here and 1 packet there. So from 1 to 2, which commodity should I send? Green or red? Green. I should send green, right? Because it makes more sense to send green, because this guy has already a lot of red. I don't want to give him more red. From 2 to 1, what should I send? You should send red, yes. Because the difference between here is 2 and here it's 3. Right? So you should send red packets here. I can do this for each of the links. Okay? So figure out what is the best commodity to send over each of these links. Okay, so then the weight from 1 to 2 is how many packets can I send from here to here. I can send 3 packets. Okay? And I can do this for each of these links. And then I compute the control action. Okay? So for clockwise controls, I will have a certain benefit based on the rates of the links, 5 or 1, and the number of packets that I can send. Okay? So I compute the benefit for each of the 2 actions. It turns out clockwise is the best thing to do. I should send packets clockwise. Okay? I do this, I take out the packets, I send as many as I can, as many as the link allows, and as many as I have available in my queue, and the packets go here. Now, if for whatever reason node 2 is a destination for the green commodity, then this queue goes again to 0. And this is how the packets arrive here. So even though I didn't do any explicit routing, the routing is implicitly part of the algorithm. Okay, so the packets, they move around, and at some point they will end up here. Okay. Any question about this algorithm? Okay, so this is a way to activate links in a network and do routing, completely distributed, no centralized knowledge, and you still have some nice optimality guarantees. All right, so when we learned about these algorithms, we thought, okay, let's apply this to transportation, but let's first see what has been done. So it turns out, and this is from a few months ago, that very few people are working on this. Okay, not so many people have tried to apply this. So there's a paper all the way from 2012, and then not much else. Okay, so I think this is a kind of nice topic to get into if you're looking for a new problem. And we have also a paper that we published recently in Transactional Intelligent Transportation Systems. Okay, so now that we know a little bit about how back pressure works and maximum weight scheduling, let's try to apply this to transportation networks. Okay, and I think now the math is over. So. Okay, so let's try to compare when we move from data networks to transportation networks, what remains the same and what changes. Okay, so I will talk about the control actions, how they differ, the buffers a little bit. I will talk about how rate is defined in a transportation network, something regarding queue states and sizes of buffers. These are some of the connections I'll try to make, in addition to all the trivial connections, right? You cannot add two cars, a car should not collide. Okay, so it turns out that one thing that's nice in transportation networks is the control actions are taken by each intersection. So each intersection decides which of the phases to activate, who can go through and who has to stop, and it doesn't need to worry what another intersection is doing. Okay? Even though there may be long-term effects, the decision is local. Okay? So basically, the very hard problem that we had in data networks of this optimization, of the maximization, you could do locally. So this is a very good benefit for transportation networks. Regarding the buffers, okay, so when you think about data networks, you have these different commodities, and I need to send the packets of this commodity over a link. When you think about cars, you have to be a little bit careful because the cars are waiting on a road, right? They have different destinations. If I want to send only those cars with a certain destination through an intersection, I mean, I cannot just pick up the cars and send them through. Right? They're physical objects, they're waiting in line. In data networks, you can have separate buffers for each destination. For cars, you couldn't do this, right? You couldn't have a huge, very, very wide road for each possible destination to have a separate road. So you need to take care of this. It turns out that when you don't do routing, you just adjust the traffic, the phases of the traffic lights, and the cars have their own routes, then you don't need to worry about this. The algorithm still works. If you want to do routing, you have to do something more sophisticated, right? Because you're looking at the different commodities. And it turns out that you can apply techniques, again, from communication networks using something called shadow queues. So you basically keep track of counters of how the algorithm should behave, and then you adjust the behavior of the cars to follow that behavior. And this turns out to work very well. When you want to do routing, I should point out that you should do communication of the car to the intersection. So the car should say to the intersection, I want to go there, and then the intersection will say, okay, good, you go on this lane, and you have to turn right. Even though maybe your destination is on the left side. That's how back pressure works. Okay, now transmission rates, and this is something a little bit interesting. When you think about communication networks, how are the rates defined? So rates are based on what we know from communication theory and information theory, so they would depend on a signal to interference plus noise ratio, they would depend on Shannon's capacity. So what is the equivalent in a traffic scenario? Okay, so the fundamental rate here would be the number of vehicles that can go through an intersection according to a certain traffic phase. That's the basic notion of rate. But because the cars are in buffers, and the buffers are the roads, there's also some dynamics on the road, right? The cars are driving on the road, so is there a difference between a road with 100 cars that are standing still and a road with 100 cars that are driving very, very fast? Back pressure doesn't make any distinction. But if you go to the transportation literature, there's also notions of rate. Right? So this is called the fundamental diagram of a road. So here we have the number of cars per kilometer on a road. Okay? And here we have the flow of the cars through that road, the number of cars passing through per hour over this road. And when you increase the density on the road, so more cars are on the road, up to a point, the flow increases. You can think of a highway, right? If you have a highway and there's nobody on the road, or just you, the number of cars per hour is going to be low because it's just you. There's nobody else. If you put many people on the road, but still everybody can drive very, very fast, you will operate along this line. This is the linear regime. And this happens up to a point. There's a so-called critical density. Okay? And that's when congestion starts. And that's when the flow starts decreasing because the cars basically have to slow down, and at some point they will stand still and nobody's moving. Okay? So this is a notion of rate that you can apply to a road or a whole city. Okay? And this is the point where you want to operate. Okay? This is maximum rate. Number of cars per hour going through is maximized. But it turns out that this point here is a very tricky point to determine. Okay, it depends on many things. It depends on the number of lanes on a road. Right? A wider road will have more maximum flow than a small road. There's the type of road, the weather, also the driver's psychology. Right? When you drive in Sweden, maybe the critical density is much, much lower than when you drive in Tehran. I think the critical density would be like way high in Tehran or India. So the driver's psychology plays a big role at this because in some places people want to take a lot of distance. In some places people can live with driving very, very closely to each other. Okay, so to optimize these algorithms, taking into account these rates would be a little bit tricky. But we try to do this. Okay, we said, let's try to do this and see what happens. And we spent, I think, a year on this. Okay, we spent a year on using this fundamental diagram, putting it into back pressure, and seeing if we could see any benefit. Answer is no. Okay, so even though maybe on an individual vehicle you can see some benefit, but for the whole system the entire system as a whole, there was no quantifiable benefit. And this was a little bit disappointing, and I think this is maybe a message to some students that sometimes you spend a lot of time on something and it doesn't work out. And that's the risk of research that sometimes you have to take. Another interesting thing is the queue state. So when you're doing transmission in data networks, you have buffers. These are the routers where you have the packets, and you know exactly how many packets there are for each commodity. When you're doing this with cars, you don't know this, right? You may have some cameras, okay? Maybe not. You will definitely have loop detectors on the highway. So these loop detectors can count for something, but none of these will typically see the total number of vehicles on a road. Okay, so you will have some uncertainty regarding the number of vehicles on the road to make your decisions in back pressure. Okay, and we evaluated this, and I'll show some results later on. Okay, finally, the infinite buffers. So in communication networks, you can assume roughly that the buffers are infinite. In traffic networks, you cannot do this, right? You will have short roads, you will have very long roads. They should behave differently. The group from Emilio Frazzoli, they've been working a lot on this area to try to adapt back pressure to account for short roads and long roads. Okay, and they made a paper that they had some very nice results. We tried to recreate these results and it didn't work. Okay, so again, the basic back pressure algorithm is very robust even against these conditions. So the length of the road has very little to do with the final performance in terms of macroscopic behavior. And I thought it was very interesting. I'll skip this. Okay, so I've been talking a lot about the basic technique and then how you should transpose concepts from data networks to car networks. Let's look at some simulation results. So this is a picture of Stockholm. Yeah, I'm sorry that I use Stockholm, but I mean it's the most congested city in Sweden, so it's with number of origins and destinations. Okay, these are some of the parameters of the simulations. So we have 24 different intersections, all signalized, 84 links, 16 distinct flows, certain maximum speed, description of the signal phases. What's important is that we simulate this not in MATLAB. Okay, we don't concoct our own city and let things run. We use a microscopic traffic simulator. It's a very expensive piece of software that's also being used by cities and municipalities to evaluate the behavior of transportation systems. Okay, so the results we have are kind of high fidelity results. They account for the driver behavior. You can see the fuel consumption of the cars. Every little detail is in there. Okay. And then we compare a number of different methods. Basically fixed signaling, okay, where the traffic phases are fixed. It's 15 seconds red, 15 seconds green, 15 seconds red, and so forth. And then some variations of max weight scheduling and back pressure routing. Okay, so this is one example of the kind of performance you see. So this is the basically the morning commute. Okay, a lot of people are entering the city. Basically 350 vehicles per hour are entering the city. And this is how the queues evolve over time. And the queues is the number of cars on the roads. Okay? So this is a case where there's actually a lot of traffic in the city. And as time evolves, there's more and more gridlock. Everybody's basically stuck in traffic. And the queues, they grow unbounded. So the system is not stable. And then with our algorithms, we're able to stabilize this system. So the queues are bounded. Okay, for the blue case here, you still have quite long queues, but the other two, very good performance. Okay. Because you say, okay, good, problem solved. But the problem was not solved. So then we looked at a different dimension. Then we saw something very strange. So now I look at the total travel time from your source to your destination as a function of the arrival rate. Basically, how many cars are entering the city per hour. So before I was showing basically somewhere here, 350 vehicles per hour. Okay, so if you look at this figure for a second and see if there's something strange. In the meantime, I'll drink some water. Okay, what's strange?
I mean, in back pressure, you drive all over the place, I guess, before you get there.
Yes.
Yeah.
So when your system is lightly loaded, okay, there's very few cars driving around, the pressure terms that you're computing to make your decision are basically very noisy. So not very meaningful. So a car will stand at an intersection, the intersection says go left. Okay, now you go right, go left, go right. So just randomly going through the city. At some point, you by accident end up at your destination. Okay?
I guess there is no information if there is not congestion in that case.
Yes, when there is lots of congestion, then the back pressure pushes you towards your destination. Okay, so your travel time will go down when there's more traffic in the system. Okay, up to a point. At some point, the arrival weight is simply so high that you're still unstable. Okay. So the story here is when you have fixed signaling, this is the red curve. So up to a certain point, you have a stable system, and then it explodes. Right? So everybody's waiting in the queues. The max weight scheduling is able to do a little bit better, and back pressure is able to do a lot better. Okay, so you could serve many, many more vehicles per hour, thinking about the future with more people in the system, and still be stable. And with very low congestion, you have this weird behavior where cars are driving around rapidly. It turns out you can close this gap, no problem. I mean, people have noticed this in communication networks. There's lots of modifications of the algorithm that are still stable, but are able to close this gap. Okay, one thing you could do, for instance, is that if you go from a source to a destination, you predefine a number of routes. Like there's only 10 routes that I'm willing to take. These are my good routes, and I only do routing according to those good routes. And then you can close this gap. Okay, what about noisy queues? What about if you don't know how many cars there are on the road? What will happen then? Okay, so here we evolve. You evaluate the total queue length as a function of time. And in blue, which is hidden beneath this orange curve, is when you have perfect queue knowledge. Okay, so you know exactly how long the queues are. This is how they evolve over time. I mean, they don't grow unstable. They don't grow to infinity. But they change over time. When you don't know the queue sizes exactly, you can still make reasonably good decisions. But your queues will typically be longer. Okay, and if you have more noise in the observations, the queue length will go up. But you're always stable, as long as your noise is finite. So this was very nice to realize. But of course, this is not desirable behavior for a system, right? So because you use these loop detectors and cameras, you will have some noise in your observations. And that means because you have poor infrastructure, you have to wait in the queues longer. So your commute will be longer. So then we thought, why can't we do some kind of Bayesian filtering to compensate for this? So we developed a particle filter operating on a state space model of a whole city, right? And then you're able to get this performance back to this. And I remember when we implemented this, Temis implemented this, he couldn't believe this. He was like, no, this cannot be that it's so good. And since then, I think he spent months learning about particle filtering, and I think now he's getting more and more convinced. Of course, this performance depends really on the assumptions that you make. Okay, so I think I will need to stop. So I believe that there's a lot of challenges for future transportation systems. Communication systems can play different roles, okay? Not just to provide the communication for the cars, but also looking at our history and our algorithms and provide inspiration to new algorithms in transportation systems. But we have to be a little bit careful when we apply those algorithms because there's lots of particularities in the transportation system that are not present in wireless communication systems. I want to thank, of course, maybe in the end, my team. These are the current people in my team, the people I supervise and co-supervise, and our postdocs that are all doing all the work. I'm just presenting. All the work is done by these people. If you want to know more about what they're doing, and I'm sure they're all cringing right now, we made YouTube movies for most of these, like 2 minutes, where each of these are describing their research. If you go to this URL, you can see for most of these their ongoing activities. Thank you.